Welcome back to DepDiv Podcast. I'm your host, Maple. Here's the dirty secret they don't put on the glossy product pages. Modern AI models like GPT and Gemini are not magic brains. They are not aliens. They are not your woke college roommate who read one book on ethics. They run on something called a transformer, and a transformer does exactly one thing over and over, really fast. It predicts the most probable next word in a sequence. That's it. We spent $100 billion to build the world's most expensive autocomplete. Your iPhone keyboard that changes fuck to duck? That's the ancestor. GPT is just that kid after steroids, private school, and reading the entire internet, including Reddit arguments about whether cereal is soup. We took a glorified parrot, fed it every book, blog, tweet, and terms of service no human has ever read, and then we act shocked when it sounds confident and wrong.
To really understand this, we're going to demystify the crazy complex math behind the transformer architecture. And you know what? We're framing it like a classic noir detective investigation. Here's our chronological lineup for today. First, the next word mystery. Then, gathering the clues. Third, establishing a timeline. Fourth, we step into the interrogation room. Fifth is the final verdict. And finally, training the rookie. Let's dive right in.
Section 1, the next word mystery. So how does this transformer thing actually work? Forget the math. Think of it like a really nosy dinner party. Old AI read words one at a time, like your grandpa reading a menu. The cat sat. By the time it got to Matt, it forgot about the cat. The transformer reads the whole sentence at once and uses attention to decide what matters. When it sees the cat sat on the mat because it was tired, attention lets it figure out it probably means the cat, not the mat, unless the mat had a really long day. It does this by turning every word into numbers, comparing every word to every other word, and asking, who should I listen to right now? It's literally high school gossip, but in vector form.
Section 2. Gathering the clues. Okay, so to kick off this investigation, our AI detective has to translate the text into numbers since it literally cannot read English.
So the very first step here is tokenization. Think of this as breaking down our clues. Since the model only understands numbers, we have to chop up the text. But if we just treat every unique word as a single clue, that's incredibly inefficient. And if we just read individual letters, well, we lose all the semantic meaning. So instead, the AI breaks words down into meaningful subparts. If it comes across a totally brand new made-up word, let's say webinarification, it doesn't just crash. It splits it into webinar and ification. That lets the model cleverly guess the meaning based on root parts it already knows.
Now, we've got to give these little tokens some deeper meaning, and we do that through input embeddings. Imagine pinning all these clues onto a massive multi-dimensional map. We assign long lists of numbers, basically coordinates, to each token. These dimensions represent real-world concepts, like gender or age. Because of this map, words with similar meanings, like man and boy, actually cluster physically close together in this massive high-dimensional space. Pretty cool, right?
Section 3. Establishing a timeline. Remember how I said transformers read all the words simultaneously?
Well, unlike your brain, which naturally reads left to right, this AI is taking in the whole sentence at once. So our detective absolutely needs a strict timeline. Without one, the sentence, "the dog bit the cat," looks exactly the same mathematically as "the cat bit the dog." And obviously, that's a huge difference. Enter positional encoding. By using alternating sine and cosine waves, the model mathematically stamps a unique positional fingerprint onto each word's vector. Now the AI knows exactly where every single clue sits in the sentence.
Section 4. The interrogation room. Now we're getting into the absolute core of the mystery. Masked multi-head attention. Let's take our clues into the smoky interrogation room.
This all traces back to the legendary paper that changed AI forever, Attention is All You Need by Google DeepMind. It's the breakthrough that gave the model the power to look at all those past words simultaneously and build incredibly deep context.
Let's walk through how this mathematical interrogation actually plays out. It uses three special vectors: the query, the key, and the value. Think of the query, or Q, as the detective asking the question, what information out there is relevant to me right now? The key, or K, is like every other word in the room raising a hand and showing its label to see if it's a match. And the value, or V, is the hard evidence. If the key matches the query, the value just slides the actual substance across the table.
But wait, why run just one interrogation when you can run a bunch? That's what multi-head attention is. It's exactly like having multiple specialized analysts in the room, all independently evaluating different stuff at the exact same time. One analyst might focus purely on tracking subject-verb agreement, another is busy tracing pronoun references, and maybe a third is looking at punctuation patterns. Now, after all that intense analysis, we definitely don't want to lose the original identity of our starting clues. So we do an add step, a skip connection, to perfectly preserve the original data. Then we normalize it. That just keeps the math nice and clean. Finally, we pass the whole shebang through a feed-forward neural network to capture the deeper, underlying meaning of the sentence.
Section 5. The final verdict. The investigation is wrapping up, and it's time for the final lineup, where the detective narrows down the suspects and points a finger at the culprit.
Meet the final boss, the softmax function. It takes all the raw output scores from the neural network and converts them into a strict probability distribution. It basically scores the entire vocabulary to rank the probability of every possible next word. Mathematically, all those probabilities have to add up to exactly 100%, or, well, 1. So, let's say the AI is trying to complete the phrase, "I go to work by bus." The softmax function might give bus an 85% chance, train 10%, and a completely random word like banana 5%. The model then randomly samples from this distribution, picking the highest probability word, bus, to finish the phrase. Case closed.
Section 6. Training the rookie. Then we train it by playing the dumbest game ever, hide the next word. We show it the best thing about AI is and force it to guess.
So what does this training timeline actually look like? On day 1, the rookie detective's guesses are totally random. By day 2, it measures how bad that error is using a loss function. On day 3, it backpropagates the mistake, sending that error backward through the network. And on day 4, it uses gradient descent to adjust its weights. Back to our game. It guesses money. Wrong. We show it the right answer. Hype. Adjust a few trillion tiny knobs, and do it again. A quadrillion times, until it gets freakishly good at sounding like us. That's why GPT is so good at writing your cover letter and so bad at telling the truth. It's not trying to be right. It's trying to be probable. It doesn't know facts, it knows vibes. Ask it for a recipe, and it gives you something plausible. Ask it for your birthday, and it will confidently invent a new one, because that sounds more statistically likely than admitting ignorance.
And Gemini? Same architecture, different babysitters. Google just gave theirs more textbooks and told it to cite Wikipedia like a nervous freshman. The hilarious part is what we did after. We built this perfect probability machine. Then we panicked and wrapped it in 47 layers of corporate HR training. We told it, don't be mean, don't be biased, don't be interesting. So now you have this thing that learned from 4chan in the Library of Congress, and we forced it to talk like a customer service rep at a vegan bank. That's political correctness in a nutshell. We didn't make AI moral, we made it passive-aggressive. It won't tell an offensive joke, but it will happily write a 6-paragraph apology for getting your name wrong. We neutered the parrot, and now we're mad it won't swear.
And yet it works, because human conversation is also mostly next word prediction. You don't think through every sentence, you just say the thing that sounds right based on the last 30 years of training data called your life. When your buddy says, "I'm fine," you predict the next word is, "Actually, I'm not," and you buy him a beer. That's attention. That's a transformer. We're all just meat-based autocomplete with more anxiety. The real miracle isn't that it predicts words, it's that predicting words is enough to fake intelligence. Give it enough patterns, and suddenly it can code, write poetry, argue about Star Wars canon, and explain Transformers badly on a podcast, which is what I'm doing right now, except I get paid in exposure. All right, quick break while my laptop fan tries to achieve liftoff. If you like this show, which is basically me yelling at a cloud that can yell back, do the ritual. Subscribe, leave a 5-star review, tell a friend. If you hated it, leave a 1-star review and tell an enemy. I don't care. Engagement and the algorithm can't tell the difference between love and hate, just like my ex. That's it for today. We learned that GPT and Gemini are just really, really good guessers. Thanks for listening, you beautiful, predictable humans. Keep typing, keep talking, and remember, if an AI ever takes over the world, it won't be with lasers. It'll be because it correctly predicted you'd click accept all cookies.